Hello dear students, welcome to the channel Pen and Paper Chemistry on YouTube. We will now take up the topic of electromotive force or EMF of a cell, right? Let's break it down to understand what we are talking about in this. Electro comes from the word electron, the carrier of charge in a conductor. Motive, motion, purpose, right? Movement. These are the different meanings which we can derive from the word motive. Force, the force which causes the movement of electron in a specific direction in a cell is what we call as electromotive force under standard conditions. Now, what is a cell? I've got a half cell here, I've got a half cell here. What do I mean by half a cell? An element in contact with the solution containing its ions is half cell. Zinc in contact with zinc ions. Copper in contact with copper ions. Zinc half cell, copper half cell. Two half cells put together gives me a single cell which we call by different names like galvanic cell, voltaic cell, Daniell cell for this particular example, right? Now, what causes the movement and what decides the direction of that movement of electrons and ultimately the direction of current as well is what we are going to study in electromotive force. I've got zinc rod dipping in a solution of zinc sulfate. I've specified over here 1 molar. Copper rod dipping in a solution of copper sulfate. Now, there is a certain potential of this electrode and we call it as electrode potential. We have spoken about it and its measurement in our earlier video on electrode potential and its measurement, where we have also discussed the standard hydrogen electrode. In case you have missed that lesson, I would request you to go through that lesson first so that your fundamentals are in place and you are able to understand this topic fully. Believe me, it's the easiest topic provided you have the fundamentals if you have understood the basics of this. When I set this up and I have also connected the salt bridge, I hope you know what is a salt bridge, what is its function. These are also discussed in a separate video. Now, when you connect them and make it a complete closed circuit wherein the flow of electrons and charges can take place easily, I'll connect a galvanometer over here and it tells me that the current is flowing from the copper electrode towards the zinc, right? So can you tell me the direction of the flow of electrons in this particular setup? Perfect. It is from zinc to copper. Can you tell me why is it so? Yes, conventionally. Conventionally, the direction of current is taken opposite to the direction of flow of electrons. Now, when I connect a voltmeter over here, to be precise, a potentiometer or a vacuum tube voltmeter, because that is going to give me the correct value or the exact value of the potential difference between the two, I get a value of 1.10 volt. We are not going into the deep in-depth study. First of all, we'll make our fundamentals clear. Then you can go about potentiometer and all those in your higher classes. So let's assume that I have connected a voltmeter over here and the potential that I am getting, observing over here is 1.10 volt. Now, the task for you is to determine which one is the cathode out of zinc and copper. Which one is acting as the cathode? What is acting as the anode? The hint here, yes, correct. We have the oil rig as the hint, correct. Oxidation is loss, reduction is gain. And the second hint is LOAN, lone, left hand side oxidation anode, and that becomes the negatively charged electrode. So 2 hints I've given you here. So you have to determine the cathode in this setup, the anode, write the half cell reactions, write the complete cell reaction, also represent this cell by means of symbols, not by means of this diagram. So every time I have to represent a cell, I will not end up making this diagram because it is quite time consuming. So we give some symbolic representations in order to show a cell. Now how will you represent this cell? If you know the answers to these questions, very good, please write them and tally with what I am going to write on the board. If, on the other hand, you have even 1% doubt about your answers or about your concepts to answer these questions, my humble request to you, is you go back to the lesson. There's another video on this channel on electrode potential, where I have explained these things very clearly, step by step, and they will make your concepts very, very firm. So firm that you will be able to teach this topic to somebody else. So if you are not clear, please pause the video now. Go to the lesson on electrode potential on this channel. Learning chemistry is easy and fun. If you are very sure and you want to tally your answers, let's go ahead. Okay, so the cathode over here, yes, because current is flowing from copper to zinc, electrons are flowing from zinc to copper. That means there are electrons over here. In other words, at zinc, loss of electrons is taking place. Loss of electrons means zinc is going to behave as the correct anode. That means copper is gaining electrons. So copper is going to behave as the cathode. Zinc in contact with zinc ions is the anode. Copper in contact with copper ions is the cathode. Give yourself a tick and give yourself a smile if you got these both right. Good. Half reactions. Yes, it becomes easy now. Because I've got cathode, there is reduction taking place. Cu2 positive plus 2 electrons gives me Cu. Now you would have noticed that I am not going into the details of writing aqueous and solid, because I find that many a times the students get confused with so many symbols. I am trying to keep it simple. Go on to anode. Loss of electrons is taking place. So zinc solid is changing into Zn2 positive, aqueous, plus 2 electrons, right? So these are the two half cell reactions at the cathode and the anode. Cell reaction. How do you get the cell reaction? You add them up. Perfect. So Zn solid, this S stands for solid state, Cu2 positive aqueous, turning to copper solid plus Zn2 positive aqueous. You got right up till now? Very good. Give yourself a star. Let's go on to the last point in this, that is cell representation. Do you remember the cell representation? Okay, so let's do the cell representation for this. What will come on the left hand side of this cell and how will you represent it? Yes, left hand side is represented as oxidation, and oxidation is taking place at zinc. So zinc solid, zinc ions, 1 molar concentration, right? Salt bridge, double slash, copper ions. Sorry, we will have 1 molar concentration over here. So 1 molar in contact with copper solid. Last thing, Yes, the direction of flow of electrons, right? So this is our cell representation. Have you got this right? Very good. You deserve 2 stars here. Super, great going. Now, so stay with me, and we are now going to calculate the EMF of the cell and how we are going to clear our fundamentals for further numericals as well. Let's see. Zinc in contact with zinc ions, copper ions in contact with copper. So we have represented this cell. Left hand side oxidation anode, which behaves as the negatively charged electrode, right? The negative end of our cell. So EMF, coming back to the main topic, EMF. What is the EMF of the cell? What is the force behind the functioning of this particular cell? What is forcing these electrons to move from zinc to copper? So there is some force which zinc is applying in order to push the electrons away. There is some force that copper is applying in order to pull the electrons. So the total EMF is the push that zinc is giving and the pull that copper is applying. That push or pull we had termed as electrode potential, right? So the total EMF of this cell is electrode potential of zinc plus the electrode potential of copper. Now we used push and pull. What is the push over here? It's the oxidation potential of zinc. The push of zinc to push away the electrons from it is called the oxidation potential. Now copper on the other hand is pulling. It wants to take the electrons towards itself. So that's termed as reduction potential of copper. Now 2 things that I need to clarify over here. I'm using the word EMF. At this level, you are also using the word potential difference of the cell. There's a difference between the two. EMF, you can say, is the theoretical value, is the theoretical force which will come into play when the 2 electrodes are connected with each other, and so the potential difference which is generated between the 2 half cells when the cell is in open circuit. That means there is no current flowing through it, is known as EMF. On the other hand, potential difference is the term which we use to measure the potential between the 2 half cells when the 2 electrodes are connected to each other. Usually, potential difference will be less than EMF. For the simple reason, I am assuming that I have to walk through this area, right? Yes, so there will be so it will be this smooth for me. But when I am walking through this area, there is a certain inhibition, there is a certain resistance that I will face on the way, which will make my movement slower than the ideal value, right? So that is why EMF and potential difference, they indicate the difference in potential between the 2 half cells. But EMF is the term when the cell is in open circuit, and potential difference is the term when the cell is in closed circuit, right? As I mentioned earlier, we will measure the EMF using a potentiometer, assuming and doing away with all the resistance that is in the way. Potential difference you measure with a voltmeter. But usually at this level, we'll call it as the same. Now, coming back to EMF, oxidation potential of zinc plus reduction potential of copper. Now, before I go ahead, now this becomes a little confusing, right? Dealing with oxidation and reduction potential. I may be talking, if you're just using the word electrode potential, I may be talking about it in terms of oxidation, whereas you may be talking about it in terms of reduction. So IUPAC, International Union of Pure and Applied Chemistry, they said, okay, let's lay down the rules of the game. And what are those rules? First, we will write all half reactions as reduction reactions. 2, we shall specify the concentration. So when we are talking about standard electrode potential, I mean a concentration of 1 mole per liter at a temperature of 25 degrees Celsius, which is equal to 298 Kelvin. 1 capital M means molarity, 1 mole per liter, and that is called standard electrode potential. Third, standard electrode potential. When I am using the word standard electrode potential, I will mean as saying reduction potential unless I specify that I am talking about standard oxidation potential, right? Otherwise, if I am using the word standard electrode potential, it means reduction potential. For example, and how do we represent this reduction potential? E Cu2 positive Cu. Basically what I am trying to indicate by this is copper is gaining 2 electrons in order to turn to Cu, and the potential at that time is 0.34 volt. If I say E Cu2 positive, now what change am I trying to show over here? Yes, I am showing oxidation. That means the potential shown over here is oxidation potential, and in that case I cannot use the term standard electrode potential. I will have to specify that the standard oxidation potential of copper is negative 0.34 volt. Now if you notice over here, standard oxidation potential is the negative of standard reduction potential. Did you notice the sign over here? Plus and minus. If this much is the tendency for copper to gain electrons, obviously its tendency to lose electrons will not be as much. It will be lesser by that much amount. Clear? When I am specifying the concentration as moles per liter, concentration is in 1 molarity, temperature condition is 298 Kelvin, and if it's a gas like we spoke about hydrogen electrode, then the pressure is 1 atmosphere. We call it as standard electrode potential, and in order to show it, we will put a small knot over here which indicates standard value, right? That means the concentration is 1 m, temperature is 25 degrees Celsius. So now we have to play the game according to the rules laid down by IUPAC. I've got oxidation potential of zinc plus reduction potential of copper. Now this is getting confusing. So let me make it simpler. I can also write it as a negative reduction potential of zinc plus, of course, reduction potential of copper remains the same, right? Now, reduction potential of zinc means the standard electrode potential, and my zinc is acting as the anode. Perfect. So I can also write it as E naught or E psi also we call it as of the anode plus E naught of the cathode, because here zinc is acting as the anode and copper is acting as the cathode, right? If you want, you can pause the video and take down these points and they become your notes, right? What can I write over here then? Let me put it more simple. So EMF of the cell, a standard EMF of the cell is electrode potential of the cathode minus standard electrode potential of the anode, right? It becomes lot simpler. Okay, I thought it's better to organize this and put it vertically so that we are able to relate to what we are doing. So E naught or E psi cathode minus E naught anode. Now cathode, which side are we representing the cathode on? Perfect, we are representing it on the right hand side. So I can also say E naught of the right hand side minus E naught of the left hand side in the cell representation, not in the diagram, but in the correct cell representation. So standard EMF of the cell comes out to, we can use two simple formulas over here, E naught of the cathode minus E naught of the anode, where these values are representing the standard electrode potential or the standard reduction potentials, right? Now it's easier, right? Because we are on the same platform. It's not that you are talking about oxidation and I am talking about reduction. That's why the golden rule is reduction. You have to start with reduction, correct? Now let's calculate the EMF of this cell that we have got at hand. So standard EMF of this cell is the EMF of the right hand side, that is copper, that is 0.34 volts, minus EMF of the left hand side. Now we had, while comparing with hydrogen electrode, we had determined that its electrode potential is perfect. 0.76 is the oxidation potential. So what is the reduction potential for zinc? Super. So you have negative 0.76 volts. Add up the two, what do we get? 1.10 volt, which matches with our observed value of the EMF of this cell, right? Do I get to see a smile on your face? Perfect. So are we ready to do and attempt a few numericals based on this concept in order to get a better stronghold of this topic? Go ahead then. Just brush through what we have done till now, and then I will take up the numericals on this topic. Also, if you notice, till now we have been dealing with the concentration of 1 mole, because I have been limiting myself to the standard values, right? The standard electrode potentials. Why are we doing that? Is because the concentration of the solution also affects the electrode potential. So further on, after taking the numericals, we will deal with that aspect of electrode potential as well, but that will be a separate video on the topic. Numerical, the most dreaded thing in physics and chemistry, right? Now from now on, what I'm going to do is I will keep adding videos on how to attempt numericals so that this numerophobia is taken care of. Honestly, yes, till the time I used to shy away or run away from numericals, I couldn't get it. But one summer break, I just sat down and then realized, you just have to analyze the question, break it down into parts, and then it's as simple as walking on the floor. Yes, you don't have to do anything in this. So I've got a question listed over here. Oh, I'm so glad some of you have already done the question while I was doing the talking. So let's tally the answers once we are done with it. For the benefit of those who are not able to clearly make out what you have to do in the question, There's an EC cell representation given over here. What is this EC? Yes, electrochemical. For this particular cell representation, you have to identify the cathode, the anode, the half cell reaction, what is the cell reaction, the complete cell reaction, and the standard EMF of the cell when the values are given to you. Now I am using the word values. You have to see whether these are reduction potentials or oxidation potentials or nothing, whether they make sense or not. If they are not, please don't do it by hit and trial. Go back, slightly slide your mouse and go back to the video around 5 minutes back and then come back to this question again. Do it yourself first and then tally the answers, and then see whether you are able to get it or not. I'm telling you, you'll really love the feel of being able to do the numerical yourself. Some of your friends will say, oh, it was so easy, you couldn't even do this easy one. Yes, it's okay. It's okay to accept we all are different in special ways. We all have our capacities, we all have our drawbacks. So it's okay to accept the shortcoming and improve on it. No worries. If you are not able to understand, go back to the video, do it again. Otherwise, let's tally the answers. Simple rule that I am going to apply over here is lone. Left hand side oxidation anode. So my anode is zinc. Simple. Cathode is lead. Simple. Half cell reaction. Zn changing to Zn2 positive plus 2 electrons. Pb2 positive plus 2 electrons changing to lead. Full cell reaction, Zn plus Pb2 positive changing to Zn2 positive plus Pb. To make it a little more fancy, put the states. So you have solid, aqueous, aqueous, solid. Yes. So half cell reaction done. Standard EMF of the cell. Just now we derived the formula E naught cell. Standard EMF of the cell is EMF of the right hand side minus EMF of the left hand side. Sorry, the electrode potential of the right hand side. Standard oxidation or reduction potentials. Yes, it's the standard reduction potential. The potentials provided to you over here, are they reduction potentials or oxidation potentials? Perfect, they are reduction potentials. How do you know that they are reduction potentials? Yes, because they are showing reduction over here. Pb2 positive gaining 2 electrons turning to lead, negative 0.13 volt. So now what is left for us to do is simply put the values. So right hand side is my lead, negative 0.13. Please don't forget the sign, minus EL, left hand side, negative. This negative is in the formula, this negative is for the value. So there are two negatives over here. So let me put a bracket in order to avoid confusion. Go ahead, open the bracket, 0.13 plus 0.76. Give me the answer and give me a smile if you got the answer right. Super, 0.63 volt is the EMF, standard EMF of this cell. Are you happy with yourself? Good. Don't worry. You'll think that, oh, this was so easy. Everybody is not the same. I'm telling you, there are children who struggle with numericals of this type as well. Now the task for you to do is to attempt, if not more, you can do more, but if not more, at least 5 numericals based on this concept. Please, for today, just today itself, do 5 numericals based on this concept and let me know your response in the comment section. Let me know if you are able to relate to them or not. Do subscribe for more videos in chemistry and don't forget to share the channel with friends and classmates. See you in the next video.